It's my pleasure to be here again. Today I will talk about how actually lazy evaluation helped us on kind of real-life application. But I will start with short recap. What is lazy evaluation, just in case someone don't remember or don't remember the details. So basically, from the definition from Haskell wiki, it means basically that things are not evaluated when we write them down and when we execute, but when we need them. So for example, when we want to print something out on the screen. And actually lazy evaluation is even not in a Haskell standard as far as I remember. What is in a standard is non-strict semantics, and lazy evaluation is one of the implementations of that. I guess that those are theoretical details. I won't go into much detail on that because that's irrelevant. So what is important is the fact that, well, things are not evaluated right away, but later. So in practice, how it looks like, I borrowed those images from a great book of Simon Marlowe about parallel and concurrent programming in Haskell. So whenever we define something like x, which is supposed to be an int, and it's supposed to be a sum of 1 and 2, so what happens behind the scene is Haskell allocates a thang, it's called a thang, which basically say that, well, the x is the result of adding of two, again, thangs, which first is the raw integer 1 and the second is raw integer 2. So as long as we don't want to print x, it remains in this kind of unevaluated form, a kind of prescription how to compute it. In a bit more complex case, like for example map, we have a list of values from 1 to 10. We apply a function to each of them and we call it x. Well, what is actually created behind the scenes is the type constructor, value constructor for list, which takes the first element as the first argument, which again is a thang, which again is this deferred computation, so f applied to x, which again is not evaluated, and the rest, so the rest of the list, so that's the applying f to the rest of the list in map. So whenever we write something like that, nothing gets computed. It will start computing that whenever we try to access those elements. For example, if we ask the head of the list, then this thing will be evaluated. If we ask the length of the list, well, it will traverse through all the list and returns us a length of the list. However, since lengths do not ask about the value of the elements of the list, those values will not be evaluated. They will remain unevaluated. Sure.
So when we ask for the head gets evaluated, or we get the tang of f applied to x? So the f is involved? Or?
Head will be evaluated what is called weak head normal form. So the first type constructor will be evaluated. Or whatever it means for a specific type, actually, because you can make a type with strict fields, and evaluating to weak head form will force those strict fields to be evaluated too. But kind of the minimal, in any case, it will do a minimal evaluation to provide you a result. So if you want to print head, it will evaluate it totally because you need to print it. But if it's something a bit more complex and you ask only for part of it, example will be later actually, then it will do only so as far as it needs to compute. Okay, so lazy evaluation is considered to be very cool because we can define, for example, Fibonacci numbers in that way. This is actually a list of all Fibonacci numbers. We start, probably at least half of you saw that, but let's go step by step through that. So Fibonacci number is a list of numbers. The first one is 0, the second one is 1, and the rest of those numbers, well, are the sum of two previous ones. So how we do it? We do zip with plus, so we will sum two previous ones. So first we take the Fibonacci numbers, all of them, and then we take the all but first Fibonacci number. And this works. This works because of lazy evaluation, because when we ask for the first element, well, it can give us it right away. If we ask for a second element, it can give us it right away. If we ask for the third element, well, to build a third element, we need two first, but we already have them allocated. So because this is constructed lazily, it can return as the third element. If you want to get a 10th element, then the same. All the remaining, all the elements from 0 to 9 have to be computed actually to get a 10th element. Well, anyway, to access the 10th element of the list, you need to traverse to that element, so it will get computed and it works. So we can have kind of recursive definition in one line. Pretty elegant.
Is the coding pattern for kind of like using lazy evaluation, like here in Haskell, like a good way, and isn't that kind of like a hack, or?
No, it's
considered a good style?
Well, good style is something kind of subjective, at least when it comes to language like Haskell, where we have very big expressive power. It depends. If you write it for mathematicians, that would be sufficient. For mathematicians, that would be elegant. If that would be something that you would like to start learning somebody coding in functional programming, in particular Haskell, and probably not on the first lesson, unless you want to make kind of show off that, well, cool, you can define Fibonacci numbers in that way. The thing is that what is considered good style and clean code is the thing whether it somehow communicates the message. So if my intention is to work with infinite list of Fibonacci numbers, then I guess that that's perfectly fine. And lazy evaluation allows you to define infinite data structures, which, if that's what you want, that's what you need, it's good. And well, I will go into details also later, because what we do is actually defining something which is not infinite, but by all practical means infinite. So, and that's useful in that case.
I have one more question. So, is such definition memorized? Like,
I think it
that's the list. That's the static value.
Okay, so it is.
Yeah. It's just a matter of
third element for the. How many additions there will be if I access third element 100 times? It will be one addition? Or?
One addition.
Okay.
Because then well, this is a list, infinite list. Which remains unevaluated. But if you evaluate the third element, it remains evaluated until you terminate the program.
So if I call the Fibonacci sequence for the, let's say, 100 element, Haskell needs to allocate all the 100 numbers?
Yes. Yes, because that's the list. That's the drawback of that. You will have all the remaining elements in it.
It's possible that this result of the evaluation might be garbage collected at some point later.
No.
No?
For lists, no, because who knows? Maybe you will access the elements of those lists later. If you have one, you can garbage collect the whole list, not the part of list.
Yeah.
Especially not the head part of the list. Okay, the other example is logical OR, something which in strict language has to be a kind of special construct supported by the language, because usually we are used to the fact that OR shortcuts, the same with AND. Thanks to lazy evaluation, well, we don't need to. Yeah. So basically, this line, the first line of definition means that whenever the first predicate is true, this can be function that evaluates to true, of course. So this can also be some big function. We don't care about the second. We just return true. So whatever was here will not be evaluated. So by the same argument, we can define if-else, which again, in strict language has to be a special construct because we don't want both branches to be executed. In Haskell, it's just a function. There is a syntax, sugar, for if-else, but well, technically you could just define a function, and it's a function. So if the predicate is true, then we take just the first expression, we return the first expression. The second one is totally discarded because it's lazy evaluated, it will never be evaluated. And the opposite for false. And well, also a kind of very classic example of how lazy evaluation allows to compose different algorithms. So we have an algorithm that sorts list. Given that Haskell is functional, then we hope that sort is implemented using heap sort. So if we want to take just first n elements of the sorted list, we write it in that way, and this will not sort the whole list, because we ask only for first n elements, and heap sort returns them one by one, so don't need to sort everything to return as first n elements. So in that case, it will result in faster runtime. Well, but life is not so nice, actually, because there is a series of examples where lazy evaluation is a problem, and again, a classic example taken from Haskell Wiki is the left fold. So the left fold is defined in the following way. So an empty list is just returns the accumulator. If this is not empty, then it applies function to accumulator and the next value in the list, and folds do fold left with on the rest of the list with this new accumulator. So what happens if we try to compute it on? If we try to sum 1 million numbers from 1 to 1 million. So let's go step by step. So well, first we apply the definition of fold. So well, the first element in the list is 1, the starting accumulator is 0, so we allocate a thunk z1, which is 0 plus 1, and we compute left fold on the shorter list with this new accumulator. Second step, well, fold L allocates a new value of accumulator, which is z2 in that case, and computes fold left on the rest. Since we did not ask for the value, it will not compute the value of z2. z2 is just z1 plus 2, the previous accumulator, and so on and so on. By that time, usually we run out of memory. But if not, then we will have a very large list of thunks, those accumulators on each step, well, and the final value. So now we start evaluating the 1 million. So what happens? This is just as a reminder where we stopped. So well, z1 million is z1 million plus z whatever. So this is it. And now this equals to that. So again we substitute. And again we substitute. So after a long series of substitutions, we end up with something like that. Nothing gets evaluated so far. We are just manipulating thunks. We did not ask for a specific value. I mean, it is getting evaluated because we asked for a specific value, but this is how it goes through this whole hierarchy of thunks that were created. So when we are here, then we can actually start computing things. Starting from here. So 0 plus 1 is 1, what's left is 1 plus 2, and so on, and so on, and so on, and so on. And if we have enough amount of memory, we end up with this result. This is what people usually call memory leak in Haskell. So due to lazy evaluation, we accumulate a lot of things which are not evaluated until some very late point in our code, and well, this results in enormous memory consumption in the task that actually requires constant memory. Okay, and this can be solved, and that's why in Haskell when we do left fold, we do a strict left fold, which basically is this is almost the same as definition of left fold with exception of this, which forces this value to be evaluated to weak hat normal form. Since that's integer, it results in compute evaluation of that. So in that case, the evaluation goes like that. So the accumulator in each step is actually computed. So this runs really in constant memory. The tricky part is that, well, it works because we were accumulating number, just one number. But if instead of z we had a pair, for example, we are summing 1 million of complex numbers. So complex number is a pair, the real part and imaginary part, or the two-dimensional point, or whatever, something less trivial. Well, then weak hat normal form will not evaluate the values, unless we explicitly asked by using bank patterns or define a data type with strict fields. And if not, then basically this history of left fold will repeat itself even if we use fold left with apostrophe. So lazy evaluation can be a problem. It can be a really big problem. So some people even hate it, or say that was not a good idea, and well, language like Idris are better because are strict by default, and things like that. I don't want to argue about design of Haskell, because actually beyond the practical mean of lazy evaluation, as far as I know, there are some deeper theoretical reasons for that, and the way the compiler works, and so on and so on. So actually the default lazy evaluation is really helpful. But I will focus on the practical side, and actually the fact that despite the fact that you need to be very careful not to get in things like that, it can be very helpful to actually write simpler code. It's easier to reason about, easier to test, and all that. So first, let me describe shortly what kind of problem we are solving. So those that were last time I was speaking here, I talked a little bit about the rules and how we build them, describing one of the algorithms. This is basically the other. But just short recap what I mean by the rule. Classification rule, so this is kind of machine learning technique to basically assign a class to data instance, which is very simple, so very easy to interpret. This is basically a predicate on a database, like a where query, where part of the SQL query, or some logical expression that picks out some rows. This is all we need to know at this moment, actually. So to decide if the rule is good or not, we need some way to score it. So we need to have a function that will, to rule, assign some number which will be that score, whatever it is, and well, of course, it depends. So it has to be some argument to that function too. Okay, so our goal is we have a database, so we want to construct the set of rules, ideally different, whatever it means, with as high score as possible, which depends on actual score definition. I'm not talking about any specific score, because there are really various scores that make sense. Okay, and for simplicity, actually, because we can build a lot of various predicates, we is not equal to or, so we can combine them in a very natural way. Since I said that we have only AND, so let's do AND of those two. So by doing AND of those two, we end up with a rule that attribute city is not equal to Tokyo, Berlin, or Warsaw, and attribute age is between 30 and 45. So this is logical OR of those, logical AND of those two rules. And this rule is a very specific one, actually, because we cannot imagine any rule which will be less complex than it. I mean, we just exclude one value on one attribute. It can be simpler. So those rules are kind of the most general, non-trivial rules that we can construct, because, well, of course, there is one more general rule, the trivial one, which takes all the rows. Okay, so those specific rules, those that have just one constraint one attribute on one value, are those rules, the more general rules. The only more general one is, as I said, this rule, which I called here top, which takes all the rows. And we have this logical AND between the rules. So how can we try to find the rules? Well, let's basically enumerate all of them and check all of them. So in that case, we are building a tree. So we have those, say that for, in real life cases, it's like between 100 and 1,000, those kind of elementary rules. Then we combine them with each other. So here we have this rule 1 and rule 2. Here rule 1 and rule 3, rule 1 and rule 4, rule... Okay, that's it. The rule 2 and rule 3, because we don't need to combine it with rule 1. We already did it here. It doesn't matter, the order. So 2 and 3 and 2 and 4. And here we have 3 and 4. And here we have a third generation, and so on and so on. Okay. So we have a tree, which is actually an enormous one, because as I said, if you have 100 here, then in the next generation you have 100 times 100, and in third generation you have 100 to the third, and so on. So yeah, it's pretty big. But that's the whole space. I mean, the solution must be somewhere here. Okay, so how to do it? How we do it? Using laziness. So how we split the problem into two parts. So the two very natural parts are, first, construct that hypothesis space, and the second, do the search. Those things are actually totally independent. I mean, not totally. But in principle, they are quite independent. And by splitting into those two parts, we actually can not only we simplify the code, because, well, right now the code is into separate parts of the whole code base, but it also simplifies thinking about the problem, actually. I mean, building the mental model of what we need to solve is, with that splitting, simpler. Because when we construct the hypothesis space, I don't care about how I want to traverse it, because there are various ways I can do that. Okay, so how to construct it? So, well, we need a tree. So, well, the data type for a tree is pretty simple to define. Actually, there is a library where it's defined, but I mean, it's that trivial. And it's a functor. The same functor like I said before. So, actually, you can derive a functor. So, this is the value at a node and the children of a node. So the hypothesis space in the simplest way would be, oh, I did not change that. For simplicity, you can imagine that R is a type rule. Actually, in real life, we have a type class, that's true, but Let's focus that this is just a rule. So it takes two arguments. So the pool of rule, this first generation of rules from which we pick the rules, and one specific value definition will be recursive because, well, 3 is the recursive function structure. So if the pool is empty, then we cannot construct any children. If pool is non-empty, then we construct a node with this r as the value. And here we need to generate all the children. So basically we take everything. So just to read it in parts, this just takes all not all subsets, yeah, but I mean, well, tails takes the list of all tails of the list, but we don't want to take the first one. And
Tails is like
sorry, we don't want to take the last one because the last one is an empty list. So we take all possible ends of that list. This corresponds to this unbalanced tree. We could make it symmetric, but let's forget it for now. So, and the function first, we map it onto those tails. So here are the tails, so the remaining parts. So we proceed recursively, but we split that tail into two elements. So we take the head and they take the rest. So the new pool will be the rest, so that we don't repeat the elements. And the new node value is this logical end of those two rules. The head of that list and the node we are exactly right at this at this moment. Okay. So we need a starting point, so we need this trivial rule which maps everything. We need to have this pool of rules, so this first generation. So then we can construct this hypothesis space, but since that's a functor, we can actually apply the score right away. So we have some scoring function. So to this hypothesis space constructed by that, we apply the score. So H space is this big, enormous, practically infinite tree, because it's so large that, well, it will never fit into memory, with the rules that already have a score in it. I slightly changed the score function. It produced this scored value. It is the rule decorated with the score, because, well, in the end we care by score, but also by the rule. So mentally, this is simple. We just declared something that we'll use later, which already have a score there, so we don't care about the score anymore. So yeah, that's, I said, this is essentially infinite. We used the algebra of rules to build that structure, and that's the last moment where we used it. Later, when we will traverse it to find the best rule, we will no longer need the algebra of rules. Actually, it won't matter if elements are rules or whatever else. I mean, for searching, it doesn't matter. for example. So examples taken from the book, how it looks like. So for example, if we have a code like that, so we say that we compute f on x with r-par and f on y with r-par, and we return the pair, then basically evaluation will work in the following way. So return will occur instantly when the things get evaluated, and those functions will be evaluated at some point, hopefully before we want to access them. If we use a sequence on one of them, then the return will wait for this sequential, but the remaining part will be evaluated in parallel. This is pretty nice because it composes quite nicely. So there is a type called strategy, which is a type synonym for a function that takes and put it into eval monad. So, well, that's quite intuitive. So the strategy evaluates something. And there is a function that takes the value, the strategy, so how it should be evaluated, and returns the value, which is supposed, this is the definition, and is supposed to actually do this evaluation. And there is a helper function that basically wraps any kind of strategy with r-par, so allows to compute it in parallel. And this allows us, for example, well, why I said that it composes pretty nicely, to evaluate list in parallel, for example. So we define a function that can take, this is the part of the library actually. We take the function that will be used to evaluate the elements of the list with some strategy, and so it will return the strategy how to evaluate the whole list. So the strategy is the argument, and here we have a list, so we evaluate value with the strategy and we evaluate the rest recursively. And then the strategy for parallel list is, we basically evaluate the list with that strategy computed in parallel, because that strategy might not be on its own in parallel. And then parallel map is just using the function using ordinary map, which produce a list, using strategy, so this produces the result. So it evaluates the list using the strategy of parallel computation of the list, and each element will be computed using this rsec. The thing is that this evaluates to weak hat normal form. The most common pitfall in using things like parallel map is that actually if f on x returns something non-trivial, some more complex object which takes time to compute, for example it returns the pair, and it takes time to compute the values of that pair, this will only evaluate the spine of it, so the pair. It will not evaluate the values. So in case of a little bit more complex structure, we need to actually tell with this strategy what we want to be computed. And what we want to be computed here, in our example, is the score of the node. So we define a strategy for the tree data type. So we have a node. This is the value of the node, because we are interested in those scored type. So here is a score and here is something, which we don't care that much actually, and the rest. So what we do, we evaluate the weak hat normal form, the score, which is a double. So this will actually compute that value. So this will force computation of the score, which is a compute intensive task because it needs to run through whole database, map that predicate on the whole database. And R0 is a special strategy that means don't evaluate. So we don't care if the rest is evaluated. In particular, we don't care if the children are evaluated. We leave them. So somehow we stick to being lazy at this moment. Okay, and we return. And the only modification that we need to apply in this find best function, this is the same function. The only difference is here. We just replace that line with that line. And this is a difference. This is the operator from this list, which basically tells that apply this function to the argument of that function. So this will apply this, this will apply this strategy to that list. So we'll compute the scores of the first generation, only that, not the children of the children, in parallel. And this gave enormous speed up, especially in BFS search, because in DFS there is I don't want to go into details, but a lot of, not everything gets paralleled. We need results sooner than they are computed sometimes. But in general it works. For BFS it works amazingly. And that's it, so that's pretty efficient. And moreover, coming back to the question, I don't know, I don't remember who asked it, about the list, if it gets memoized or not. So basically, the tree is a static structure. So when we are doing, for example, iterative search, so when we are at, for example, at the third iteration, the first and the second iteration are already computed, so it's pretty fast. We don't recompute the score because we computed it. Okay. So the conclusions, what we observed is that actually with this lazy evaluation we get code much faster than the Python code. By factor 10 to 100, more or less. It depends on the data set. Actually, there were bugs in the Python code discovered during implementation of the Haskell code, so it is pretty hard to compare because those bugs were basically resulting in the fact that some part of hypothesis space in Python were not searched. And the fact that Python is not good at parallel computation is not something is not surprising. But anyway, we are much more efficient when parallelizing that. The code is now much easier and much more tested. It is much more easier to test it, and moreover, we actually tested a lot of variants of those algorithms: how to build a hypothesis space, how to prune it, how to traverse it, how to update things, and all that was possible thanks to the fact that we were able to separate those things, the construction of hypothesis space and traversing it into separate parts. And that's it, thanks.